Hi there and welcome from Ventura, California to today's webinar, Autonomous Week Day 1, Inspection and ISR, sponsored by Inside GNSS, Inside Unmanned Systems, Spirent Communications, and Vector Nav Technologies, and hosted by WebAttract. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders as today's webinar features expert insights and key technology aspects of sensors, platforms, and integration for implementing autonomy. Today is day 1 of our 3-day series, which focuses on mapping, surveillance, and intelligence, surveillance, and reconnaissance, also referred to as ISR. Now, we've invited you, along with over 450 professionals registered across 52 countries, representing a variety of industries. Over the next 90 minutes, regardless of your industry segment or your location, we're confident you'll find today's webinar value. Before we get started, Richard Fisher, publisher Inside GNSS and Inside Unmanned Systems, would like to take a moment to welcome you and introduce our main moderator for today. So over to you, Richard.
Thanks so much, Lori. On behalf of Inside GNSS, Inside Unmanned Systems, Vector Nav, and Spirent Communications, I extend a warm welcome to our audience from around the world for day 1 of Autonomous Week. Now, Autonomous Week brings our industry-leading webinar series, running continuously for 11 years now, to the next level. The speakers are well-rehearsed. The content is excellent. The presentations have been curated and harmonized for your expert consumption. So we appreciate your attention and participation, and we're delighted that you're with us today. So thanks all. Now, I'd like to introduce our moderator for today's webinar. He is the editor-in-chief of Inside GNSS and the PNT editor for Inside Unmanned Systems, Mr. Alan Cameron. Alan, the floor is yours.
Thank you, Richard, and welcome to everyone around the world. Thanks to our sponsors for this webinar, the first of 3 in a jam-packed, action-packed week of virtual technical education. Our sponsors today are Vector Nav and Spirent, and we'll be hearing from General James Poss, U.S. Air Force retired, from Jeremy Davis, Director of Engineering at Vector Nav, and Arthur Neves, in charge of Aviation Business Development at Spirent Communication. As Richard said, this is a curated set of webinars tailored for your maximum not only enjoyment but education. We have seen, Richard and I, a burgeoning of online content available in this unusual and very challenging era, and we appreciate your attendance at ours, which I am confident you'll find of the highest quality of anything available online. Lori, let's find out a little bit about our audience, if we can.
Absolutely. Go ahead and take a look at our first poll question here, and interested to hear from everyone in the audience today. What is your primary interest in or application of autonomous flight? And we're looking for you to select one answer. Intelligence, surveillance, and reconnaissance, or ISR, for defense or military. ISR for non-military public safety security use. ISR for commercial security or asset tracking monitoring. Purposes other than ISR. So it looks like 24% saying ISR for defense or military, 25% ISR for non-military public safety security, 17% saying ISR for commercial security or asset tracking monitoring, and our front runner here, 34 purposes other than ISR. And if you do have some of those purposes in mind, you're welcome to put them through the question panel as well. But Alan, thoughts here?
Well, it's great to see such widespread background, interest, and application. Of course, autonomous flight has many, many different applications, but as we know today, we're focusing on ISR, although 34% of our audience do not despair, because there's plenty of content here that is widely applicable to every aspect of autonomous flight, no matter what you're trying to do with it. We have 3 experts whose expertise extends into many different realms of autonomous flight. And let's proceed now to hear from the first of those speakers, General James Poss, retired from the U.S. Air Force with the rank of Major General. He is CEO of ISR Ideas. ISR Ideas is an intelligence, unmanned aerial systems, and cyber warfare consulting firm. General Poss is the founder and former executive director of the Alliance for System Safety of UAS through Research Excellence. That's ASSURE, and that's the FAA's Center of Excellence for Unmanned Research. He's a 30-year U.S. Air Force veteran with combat experience in 4 wars, and he was the Air Force's senior career intelligence officer at his transition from active service in March 2013. He's a leading expert on UAS, having helped design the Air Force's remote split operations systems for UAS control and the Distributed Common Ground Station for UAS intelligence analysis. General Poss also has extensive experience in cyber operations from his assignments with the National Security Agency and as the Air Force lead for stand-up of U.S. Cyber Command. General Poss, please proceed.
Well, Alan, thank you very kindly for that introduction. I mean, I could kind of summarize that for everybody and explain my role here. You could boil it down to old guy. And I'm about to give you the old guy setting up the importance of positioning for ISR as we go through. So any discussion on modern positioning with GNSS and fantastic inertial navigation units has to go back to the old days when I first joined the Air Force, when we really didn't have any of that. So let's go back to what some people are calling Cold War I back in the 70s and 80s and discuss how we did positioning for ISR then. So I'm going to pick on what we used to call back then the TR-1 Dragon Lady, which was based on the old U-2A of Gary Powers getting shot down over the Soviet Union fame. We updated it, put a new engine in, and put those super pods on it. You can see the big pods there for various sensor systems, and most importantly, put a link on it. Maybe if Gary Powers had a link, he wouldn't have got shot down, but the TR-1 certainly had one. So 99 times out of 100, the TR-1 flew linked to a ground station for real-time ISR, which is good because we learned in the 70s how to use the surveyed-in link points to be able to tell exactly where the aircraft was. So we knew where the link points were. We knew exactly the azimuth and angle of the antennas. The antennas would give us range to the aircraft, and when all of that was working properly, and it usually was, we can get accuracy down to 100 foot, which was pretty good for back in the day. Now, we did fly the U-2 off-link occasionally, and this is where we're getting a little bit more applicable to what we're dealing with here with modern manned and autonomous aircraft. So when it was off-link, like when we were flying for Desert Storm, it actually had an LNS-3, which is the inertial navigation system, and I'll talk about that a little bit later, was manually updated by the pilot. They had a scope that still have a scope that looks down through the bottom of the aircraft, and when he would pass over a known point, like a runway somewhere, he could update the link, and you'd get accuracy to about 500, fairly accurate stuff. Most of the time, they were relying on astral trackers. U-2 flies above 60,000 feet, so you can see stars up there. And that was actually pretty accurate down to about 500 foot or so. So a little bit of word about inertial navigation systems. So it's an American invention. We invented it in the late 50s. Back in the day, when I first joined the Air Force, an INS was a bunch of accelerometers and gyros, which measured the aircraft acceleration. The air computer would then figure velocity, and you would have a position for a certain amount of time between updates. In the case of the LN3, you'd have about a 2 nautical mile circular error probability after keeping it on for an hour. And generally what we would do is, in the U-2's case, would be updated either manually or by the star tracker. Despite my best efforts, I could not find how big the LN3 was. I've talked to a couple of former U-2 pilots. They describe it as huge. So I'm going with much bigger than a bread box. All right. So after that, after you get the aircraft positioning, you also have to talk about the unique needs of the sensor. So two types of main sensors that I can talk about on there. First is the electro-optical IR sensor, which if you can kind of think of, you're in the back of a pickup truck and you've got a telephoto lens on. In order to figure out what you're taking a picture of outside that truck, you're going to need to know everything about the truck's position, or in this case, the U-2's position. Where is it in altitude, XYZ coordinates, pitch, yaw, roll, that's all important. Because you also need to know what pitch angle and azimuth the camera is pointed at, because you're not asking to geolocate something where the aircraft is, you're asking to geolocate something where that camera is pointing. So that's why location was so important for us, particularly the electro-optical sensors. Synthetic aperture radar, which we used a lot, was actually a preferred sensor back in the day, number one, because it saw through any type of weather, and we predominantly flew this aircraft over the inter-German border. But also the sensors would always give you accurate range and azimuth to a target, as well as altitude, which would allow you very accurate geolocation without having to wonder about all the higher math you'd do with an electro-optical system. All right, so that's the old guy portion. Let's go into the middle-age portion of this and talk about when I first started flying with drones back in the year 2001. How we do it with these large drones flown by the Air Force. And we're going to pick on the penultimate large drone out there, which is the General Atomics MQ-9A Reaper, which is based on the older MQ-1, which was developed in the mid-90s. Reapers came around in the early 2000s. As you can see from the aircraft there in the lower left, it's got an electro-optical infrared sensor ball on the front, the big round thing. Can't really see the Lynx synthetic aperture radar. It's kind of hidden by the wings, but trust me, it's under there. And then a variety of weapons. Looks like we're packing 4 Hellfires on that one, and a variety of other stuff. The MQ-9 has to maintain link with a ground control station in order to operate. It can go off link, but that's generally a bad thing. You can tell it to bore a hole in the sky, and if you trust it to do that, it'll do that. But generally, when it's off link, it's going to wait for a while to try and acquire link, and then it's going to try and make its way home as best as can autonomously. So aircraft positioning now between the 70s and 80s, and we're talking the late 90s, the United States Air Force has invented the global positioning system. Can I get a thank you for the Air Force? Oh, wait, you guys can't talk back. But anyhow, if you could, I'm sure you would be thanking us now, but I'm not going to go into how GPS works other than to say it does. So instead of getting at best 100-foot circular error probability where the aircraft is, you're going to get well within 3 meters, on modern aircraft. It's also hooked up to a modern inertial navigation system. So instead of being this giant collection of gyroscopes and accelerometers on the MQ-9, it uses a laser ring INS. So the laser is shooting around in a ring on the INS, and the sensor detects very slight motion in the laser due to aircraft acceleration. The computer calculates velocity. And not only is it very accurate, but the position decays at, I'm not going to do math in public, but a lot slower than it did for the old accelerometer gyro-based INS, so about 0.2 nautical miles per hour. I was able to find this, so it's 7 by 7 by 9 inches, about 20 pounds, so slightly bigger than a bread box, but not small by any means, so it would have to go on a medium-sized aircraft like the MQ-9. Sensor positioning. Again, we have the same physics problem that we had with the U-2. The primary sensor on the MQ-9 is the EOIR sensor, that sensor ball up front. Everybody's seen it on TV and on the internet and everything. So the problem we've got is we are constantly having to do some pretty higher end math to see where that sensor is looking at. And the sensor's got a range of, gosh, no math in public, about 15 nautical miles or so, depending on the target. So you're looking way off of nadir and where that aircraft is. So it's very, very important that you get accurate pitch, roll, yaw, attitude, as well as the geolocation of the aircraft. And we'll go into that in more detail with a couple other speakers. The synthetic aperture radars are pretty good. The same as with the U-2. It's going to give you great range and altitude, which is going to allow very accurate geolocation. If you can get a United States Air Force crew to turn that daggum SAR on, please call me. They rarely use it. Don't have that problem with the Royal Air Force guys. They love it, but it can be used to update the position of the aircraft too, if need be. All right, so now we're into kind of the small swarming drone world that we're talking about, and we're in an entirely different physics problem. No longer are we flying around in the MQ-9, but we're flying around in much smaller aircraft. And on the lower left, I'm Air Force, so I picked artist's conception of DARPA Gremlin aircraft there. But there's a whole host of small UAS out there. The Army uses the Raven, fairly big Shadow, about the size of a Volkswagen, air-launched effects, which are meant to be launched from either an MQ-1 or from a helicopter. So they're very small. Navy and Marines have the Scan Eagle, again, about Volkswagen size, Puma, model aircraft size, and then the Blackjack, a bit bigger than the Scan Eagle. Now, the Air Force, if this had been 10 years ago, we wouldn't have been too interested in small UAS, but all of a sudden, we've realized that we're coming up against some very, very highly defended airspace, probably. And one of the ways we want to get around that is to swarm, and you can only swarm affordably if you're using very small drones. The Air Force word for them is either expendable, which means you're not getting them back, or attritable, which means you're going to get them back 5, 6, 7, 8, a couple dozen times. And so we've got the Gremlin, which is an air-launched and air-recoverable drone that we're experimenting with DARPA. The Paradix, which is a Lincoln Labs MIT product, it's so small it actually fits in the flare tube of a fighter, and you launch it out and it flies for about an hour, mainly jamming. And then the big one that everybody is going after now, LCAPS, the low-cost attritable aircraft platform. But these are all small aircraft. They're nowhere near the size of a U-2 or the MQ-9 that we've used before. So generally, you got GNSS and INS, and that is it. There's not, if you're going to make an attritable aircraft, if you're going to make the aircraft small, if you're going to make it attritable, you're not going to have money because you don't want to put an awful lot of expense into it. If you're going to make it small, you don't have very much of the most expensive stuff in aviation, which is size, weight, and power. So these guys, it's either GPS or really nothing. Now, true, if some of these have EOIR sensors, and not all of them do, if you can get the picture back to an analyst, the analyst can geo-register where the picture is using a known point, but you're completely dependent on GNSS, INS otherwise. We do some old-fashioned terrain matching, which is what we used to do in the air-launched cruise missile world back in the late 70s and 80s, where the aircraft takes off with known terrain models and it turns its camera on and compares the terrain. But that's very limited, and it takes hours to plan those attack routes. Now, of course, some of these aircraft, like I mentioned, the Paradix, are for electronic warfare purposes, so their absolute location isn't as important as their relative location to the radar. So they're going to do stuff like take off, use your sensors to find a radar, home in on the radar and blow it up or jam it. So not quite as important for those type. All right, so what do we do about it? What are some of the issues that you got when you're just relying on GNSS anyhow? We really didn't have an awful lot of experience with interfering with GNSS until Syria. The Iraqi war, we had some jamming, but the fact that the last jammers were destroyed with GPS-guided weapons probably tells you how effective they were. Can't go into detail on what's going on in Syria, just to say that there's lots of press reports about GPS jamming and other types of electronic warfare stuff going on in Syria. So the problem it causes us potentially, if in the MQ-9, again, a fairly large aircraft, you're either going to make the crew update the INS using the synthetic aperture radar, using surveyed points, so they're going to have to, fly within range of an airfield or a radio tower or something we know the exact range of. If we go lost link, that's an even bigger problem. Keep in mind, when the MQ-9 goes lost link, it's going to orbit around for a while trying to establish it, and then it's going to go home. Well, if you're in an area with GNSS interference, you're probably going to have to go home pretty quickly before your INS decays to a point where you won't know where home is. Small UAS, they have severe mission impact because of the swap constraints, size, weight, and power. They just don't have the size, weight, or power that you would need to put in a big laser ring gyro like you do in the MQ-9. So countermeasures, we got a variety of them. Actually, most aircraft GNSS antennas are on top of the aircraft. They're shielded by the airframe itself, so it's a lot harder to jam them than it sounds. And on top of that, we've got a variety of different sensors antennas that can null out jamming and whatnot. We also can mission plan for jamming. If we know about where we're going to get the jamming effects, we can plan that our INS is going to decay at this rate, so you're going to have to leave the jamming area, come back in and get an update, refresh your INS, that kind of stuff. Training is a big deal. I can remember the first time we tried to train with GNSS jamming back in the mid-2000s. It was funny. You could spot the under 30 crowd flying F-16s because they would go to rendezvous at the waypoint and they would be off by 5 or 10 miles because they hadn't been checking to see if their nav position was decaying. The over 30 crowd checked that obsessively and updated their position using radar. Small UAS, I'm afraid I'm going to have to call a friend on this one. I'm not sure if we really do have a good countermeasure now, other than the suggestions that Vector Nav and Spirent are going to bring to us out here. So like the rest of the audience, I am really waiting for what these guys are going to say that is going to give us some ability to maintain our vital navigation position, even though we're having GNSS countered in one way, shape, or form. So, all right, that's enough for the old guy side. Alan, I'm going to turn it back to you, and hopefully we're going to hear some solutions.
Thank you very much, General Poss. Boy, Raven, Shadow, Scan Eagle, Gremlin, Paradix, LCAPS. I don't know if anyone has the wealth of knowledge of military platforms that you do. Of course, you can't talk about it or else we'd have to do something drastic to you. But what you can talk about is of great value to the audience. I do see some questions coming in for you, and we'll turn to those in another 10 or 15 minutes. A couple of questions just at a break midway through Jeremy's presentation. We'll hear now from Jeremy Davis, Director of Engineering at VectorNav, where he has focused for the past decade on high-performance inertial navigation solutions using the latest inertial sensor and GPS GNSS technologies. Jeremy holds a PhD in aerospace, aeronautical, and astronautical engineering from Texas A&M University and has particular expertise in orbital mechanics, simulations, and robotics. He is the author of The Inertial Navigation Primer. Jeremy, take it away.
Thank you, Alan. And thank you to General Poss for that great introduction to aerial ISR over the last 50 years. I'm going to follow up on his comments with a look at the role GNSS-aided inertial navigation systems specifically play in aerial ISR. Now, I could talk about this topic for hours, so I really encourage you to follow up after the fact. We have quite a collection of resources covering aerial ISR and are more than happy to discuss your application. Now, as General Poss noted, there's been quite a remarkable evolution over the last 50 years in the aerial ISR space, starting with something like the U-2 manned systems flying at 70, 80,000 feet and able to go halfway around the world, and down to today, hand-launched UAVs that can provide reconnaissance just over the next hill. And you can really look at this chart in a few ways. Obviously, first is the evolution over time from the U-2 on down, but also, as I mentioned, a drop in altitude and therefore scope from a more global perspective down to a much more localized one. And finally, the dramatic reduction in size, weight, and power swap that continues to this day. And one of the things that has enabled these much smaller systems has been a revolution in navigation technologies over the last 30 years. What I'm talking about here, as General Poss mentioned, is the explosion through the 90s and 2000s of two complementary technologies in navigation, which are GPS and MEMS inertial sensors, MEMS being microelectromechanical systems. And as you can see, both have somewhat seminal moments in '93, which is when GPS becomes fully operational, and Analog Devices releases the first mass-produced MEMS inertial sensor, just the single-axis accelerometer. And over the next 2 decades, both advance in just leaps and bounds. Couple highlights: selective availability gets disabled in 2000, so the positioning errors dropped from tens of meters to a couple meters. A few years later, Crossbow releases the first FAA-certified attitude and heading reference system, or AHRS. And then by 2009, technology has advanced to the point that VectorNav is able to bring to market the first AHRS on a chip, the VN100. But as I mentioned, what's truly revolutionary is how these two complement each other when they come together. You have an emerging inertial technology in MEMS that can only track for a few seconds at best, especially in the early days, paired with a new positioning technology in GPS that provides you an update every second. And when you put those both into a single sensor like the VN200, what used to require an INS bigger than a bread box and costs you 6 figures, you can now achieve with a chip the size of a postage stamp. And that dramatic advance in SWaP has been critical to the development of today's unmanned systems. Now, what roles exactly do GNSS-INS systems play in aerial ISR? It comes down to 2 things: primary navigation of the aircraft and being able to point the sensing payload. We'll start with the second one, which is pointing the sensor package. So let's say that you have an aircraft flying around with a gimbaled camera and you spot an object of interest on the ground. That image alone has limited value unless you can put real-world coordinates on that object, which is a process known as georeferencing. Direct georeferencing in particular uses the position and pointing information from a GNSS-INS to directly map from the ISR sensor to the spot on the ground. Now, the accuracy of that solution depends on 3 things. First, the performance of the ISR system itself, the camera or direction finder or radar, and of course that's determined by the current state of the art for those different technologies. The second aspect is the accuracy of the position and attitude solution coming from the GNSS-INS, which we'll get into on the next slide. But the third aspect is often overlooked, and that's the integration of the two. You can have a perfectly calibrated camera, a high-end inertial sensor that knows exactly where it is and where it's pointed, but if you haven't accounted for the mechanical and timing offsets between the two, you're not going to get an accurate result. It gets even more complicated if you have a gimbal involved. And those integration errors can swamp the errors of the individual systems if you're not careful. So VectorNav has developed an entire suite of application notes and software tools for tackling those alignment problems. Now, I can't get into it a lot today because every application is different, but please follow up afterwards and our team can make sure you've got what you need. For now, let's turn our attention to the impact of the GNSS-INS directly on the georeferencing solution. Now, the GNSS-INS provides 2 things, positioning and pointing. So let's start with positioning. Obviously, to map an object on the ground, you need to know where you are when you take a measurement. The positioning performance comes down, in most cases, to the accuracy of the GNSS system itself, which is typically 1 to 2 meters. There's also a technique known as real-time kinematic, or RTK GNSS, that uses a base station transmitting real-time corrections to what's called the rover, which in this case is the UAV, to improve to just a couple centimeters level of accuracy with RTK. Now, critically for an ISR application, there's a 1-to-1 mapping here between your GNSS positioning errors and your georeferencing errors. If your aircraft position is off by a meter, then your mapping of the point on the ground is going to be off by a meter. Of course, the other critical part is pointing or attitude, which is driven by the INS performance, the inertial performance. And there are generally 2 different performance grades of inertial sensors that MEMS currently occupies, and that's industrial grade and tactical grade. And as you can see, both can provide very high accuracies depending on the particulars of your application, especially when integrated with a GNSS receiver. But there is a 5 to 10x performance delta between the two that can be critical. the next question then is, how do those pointing accuracies of these INS map to your spot on the ground georeferencing? And that comes down to the distance between your sensor and the spot on the ground, which we refer to as the slant range, or sometimes simplified as just the altitude. And you can see on the right how there's an inverse relationship between the required pointing accuracy and altitude for a particular georeferencing accuracy. So we plotted here if you want 1 meter level georeferencing accuracy. Pointing requirements here go from about half a degree at 100 meter altitude down to 0.05 degrees at a kilometer. So the altitude really drives the inertial performance requirements as you're designing your system. Now, I want to give you a quick example that we run through in one of our application notes to give you an idea of how all of these things come together in a real-world situation. So here we have a gimbaled camera system flying at 1,000 meters at a kilometer altitude, and you can see that we've modeled some of the camera errors, some of the alignment errors like timing, jitter, and of course the GNSS INS errors. And what you see here on this slide now are what we call error ellipses, which is basically the accuracy of the georeferencing solution once we account for all of those error sources. The dotted lines show the performance given RTK GNSS, while standard GNSS is given in the solid lines, and then industrial versus tactical grade performance is shown with the tactical grade in red and the industrial grade in black. And this just gives you some insight into how those individual system numbers that we're talking about end up mapping to point on the ground performance and which is what you're really interested in. So that covers sensor pointing. In a few minutes, we'll discuss navigating the aircraft even when GNSS is unavailable. But for now, back to Alan.
Thanks, Jeremy. We'll be back to you in just a few minutes for the second half of your presentation. We're going to pause a bit just to stretch our mental muscles and field a couple of questions from the audience. First ones come in, excuse me, for General Poss. How do GNSS INS products fit into prospective FAA UAS performance-based standards? I know there's been a lot of formulation of those standards, a lot of debate and so forth. Where GNSS and INS products fitting in there?
Yeah, so that's a tough one. Back in the old days, 3 or 4 years ago, there was a separate set of specs, for components that would be, used as part of an airworthiness determination for aircraft or, type certification for an aircraft. For UAS, there are currently no type certification standards that are published solely for UAS. True, the FAA is looking at about 30 or so different unmanned systems for type certification, but they're using the manned aircraft certs, and then they're just going to waive the portions of that are not directly applicable to drones. So believe it or not, there's a requirement that all aircraft have seat belts on board, for example, which you don't need on a drone. There are rumors that the FAA is going to come up with UAS-specific systems, and they're going to be performance-based characteristics vice the old compliance measures that will take about 9 foot of paperwork in order to get an airliner done. But the jury's still out on what's going to go with that. To be honest with you, I'd be interested to hear, Jeremy and Arthur, what you guys think about your products. And I mean, are you guys aiming to get yours FAA certified?
Well, I think that's a tricky question. We're certainly staying abreast of the situation. As you said, General Poss, there hasn't been a lot of clear guidance coming from the FAA in terms of how that's going to progress in the unmanned space and which standards and which requirements they're going to include. So, for the time being, we're kind of in a wait and see approach. We don't want to go running after every different iteration that the FAA floats out there, but hopefully we'll see some convergence on that soon, and then we can take a look at that.
Yeah, I just wanted to add that certainly the standards are rapidly evolving, and I'm sure all of us are helping work that. But one of the things that's a little bit different in the UAS world, in the case of manned aircraft, the GNSS performance is well defined in the radio navigation plan, where you have different limits for different phases of your flight, whether it's approach, landing, or en route. In the small UAS, there's such a wide variety of metrics. For example, you may need centimeter level resolution for some applications, and you may only need meters for the others. So I think it's still an evolving field, but it's also very exciting.
Yes, as Arthur said, evolving. The use of the terms rapid and FAA in the same sentence may seem a bit of an oxymoron, but we do want to proceed carefully, and a lot of people are watching, a lot of people are waiting, and a lot hinges on the outcomes. General Poss, back to you. Can you assist customers in making safety cases to the FAA for use of their products?
Yeah, you've hit another FAA fault line. Now the FAA is used to dealing with airliners that really don't change that much over the years, and airlines that certainly don't change that much when you're talking about dealing with procedures, what the airlines are going to do versus equipment, which is what the aircraft is going to do. So they're used to being able to take their time on and decide, what is a good safety case to approve or not. Drones change all that. They move so quickly. They're used in so many different types of operational contexts that it's really causing the FAA problems in trying to decide what's good or what they're going to approve as a safety case or not. The FAA is infamous for its bring me a rock style of approving waivers, and the joke is you'll come in and spend months and millions of dollars working a safety case for something, and bring it to the FAA, and they'll look at it and say, wrong rock, bring me another rock, bring me another safety case, and really don't give you a lot of feedback in doing that. To be honest with you, I'd be interested in hearing what Jeremy and Arthur would say about that, because I mean, you guys are actually hands-on, having to work with your customers and get through the FAA on this bring me a rock question, I'd assume.
Yeah, I mean, I think, as I said earlier, it's, and as you mentioned, it's definitely a real challenge that the industry is facing at a top level here, where there's kind of some shifting goalposts and not a lot of clear guidance, and kind of a we'll know when we see it kind of attitude, perhaps, that makes it difficult to kind of proactively address those safety concerns. So it's I think every case that we've worked on with that has been very different in terms of how it was handled and how it was approached.
All right, Jeremy, question for you. VectorNav recently launched a tactical embedded line of IMU and GNSS-aided inertial products. What's the suitability of these products? What makes them a good choice for ISR pointing and navigation?
Yeah, absolutely. So, and I'll talk about this a little bit more in the second half of my presentation, but, the main thing with the tactical embedded is we've really pushed down the swap, size, weight, and power, and cost that you can achieve tactical grade performance for a GNSS INS into a dramatically smaller package, and that's really going to work to the advantage of anybody doing smaller UAVs, whether they're looking to just point the payload or for primary navigation of their UAV. It's really going to push out what's possible for smaller aircraft to maintain higher levels of accuracy, especially in GNSS challenged environments, I'll say.
All right. We're going to go back to Jeremy in just a moment, but first, Lori, let's turn the tables on our audience and ask them a question.
Okay. So on your screen is that poll question. And I'd like to hear from all of you. What is your primary concern in the use of positioning navigation, and timing technologies in UAS. Availability and accuracy, reliability, continuity, integrity, or safety compliance. All right, 52% with availability and accuracy, 23% reliability, continuity, 16% integrity, 9% safety and compliance. Thoughts here?
Well, we did, for a hardball question, it's really a bit of a softball at the same time, because we did lump the two biggies together, and that turns out to be the clear leader. Availability and accuracy. You got to have them. Without them, you're pretty much nowhere. Although, you know, reliability and continuity, important as well. Integrity, less of a concern perhaps in UAS than in piloted aircraft, at least at this point. And safety and compliance, well, as we just heard from our experts, comply? Comply with what? Clear standards are still lacking. Well, let's go back to Jeremy, and let's hear more about the role of inertial and GNSS and the importance of SWAP in UAS navigation. Jeremy?
Great, thanks, Alan. So what we'll jump back into here is using GNSS-INS for primary navigation of your unmanned system. Obviously, this really applies to any unmanned aerial vehicle, not just ISR ones. And there's a few things that come into play. The first, obviously, is accuracy, as primary concern. We was just in that poll. What you'll generally find here is that an industrial grade INS is typically sufficient to keep the plane in the air, but a tactical grade sensor can reduce your overall SWAP by pulling double duty, both flying the UAV and pointing the sensing payload. The other major advantage is that tactical grade can be critical in situations where GNSS may be lost, which we'll get into more in just a moment. Another often overlooked aspect of GNSS-INS accuracy is the algorithms employed. VectorNav sensors have gone head-to-head with a wide range of competitors at double or triple the price point, but come out ahead because we make better use of the sensor data available to us. So keep that in mind. It's not just about the what's on the spec sheet for the inertial sensor. The second thing to consider is in primary navigation is system timing. The controllers required for high dynamic systems like small UAVs rely on low latency, high update rate feedback, and in fact they require it to maintain system stability, so it's critical. The third aspect is, of course, size, weight, and power, SWAP, and the less of each of those that you spend on the navigation system, the longer your flight duration, or the more you can devote to the sensing payload. As I mentioned during the Q&A, the tactical embedded that we just released, pictured in the upper right there, is really a game changer in regards to SWAP for a tactical grade GNSS-INS. Finally, reliability is really key here. Failures of the navigation system can easily lead to what's probably my favorite euphemism, unexpected ground interactions. And because these smaller unmanned systems continue to push the performance envelope, both the hardware and the software needs to be up to the task. So let's talk a little bit more about that reliability through an expanded performance envelope, especially in those moments closest to the ground at takeoff and landing. VectorNav has worked with a wide range of UAV manufacturers, from startups to major defense contractors, pioneering the navigation technologies required to enable some of these advanced concepts in ever smaller UAVs. The first is VTOL, or vertical takeoff and landing. Just like in manned aircraft like the V-22, the transition between vertical and horizontal flight is one of the most treacherous in aviation. Your navigation solution needs to be rock solid. You need a GNSS compass to maintain accurate heading in the static and low dynamic regimes, and advanced algorithms that can smoothly handle the transition to higher speed flight. The next thing is catapult launch UAVs, which experience relatively high long duration shocks, something on the order of 50 to 100 Gs for 10 to 20 milliseconds. At the end of that shock, the navigation system has to align almost instantly. The UAV is close to the ground. It's just above stall speed. There's not a lot of time for the INS to get its bearings. Certainly, there's no space for S-turns or figure eights that some of our competitors require for heading alignment. We've carefully designed our algorithms to track with only the data we can extract from a typical flight profile and not require any additional maneuvers. Finally, tube-launched vehicles, which are typically air-launched, share the same shock and rapid alignment requirements as the catapult-launched UAVs, but it's an even trickier problem to solve. With the wings folded, the aircraft comes out tumbling or at least rolling. If you're launching from a fixed-wing aircraft, you're probably launching at speeds exceeding your own cruise speed. GPS is typically unavailable inside the tube. So our systems use high bandwidth, high range inertial sensors to track those high dynamic motions at launch, and then our firmware supports various ways of transferring GNSS or INS data from the host aircraft to the UAV pre-launch so that we're tracking within seconds of leaving the tube. Now, of course, successfully getting airborne is only part of the challenge. Once you're flying, you may have to contend with degraded GNSS environments. So let's talk about that a little bit. So the first that we'll talk about is multipath environments. And for those not familiar, multipath refers to situations where the GNSS receiver may be tracking reflections, which are the black lines, in addition to the direct signals from the satellites, the red lines. This can lead to huge errors in the measurements reported by the GNSS, and a simple Kalman filter implementation of a GNSS INS is going to still struggle to track. Of course, multipath can occur in a real canyon or in an urban canyon. So here we show how our sensors handle downtown Dallas, where VectorNav is headquartered, during a drive test. You can see that the GNSS reported altitude is off by 100, 200 meters at times. It's obviously catastrophic if it were a UAV. But with VectorNav's proprietary algorithms for rejecting those bad measurements, we're able to track right through it with the help of the INS. Now, another common GNSS challenge environment is one subjected to intermittent or short-term GNSS outages, whether that's from natural causes like flying under a bridge on an inspection or something like inadvertent jamming. The good news is that MEMS inertial sensors can keep the UAV on track during those brief outages. I'd love to show you some examples of this happening during an ISR mission, but the best example of temporary GNSS outage that I'm free to share is our work with the Red Bull Air Race. So here's a quick video. If you're not familiar, the Red Bull Air Race was a time trial event where each pilot flew through a series of slaloms and gates as fast as possible. There were time penalties for missing certain marks on the course or pulling too many Gs, which is where our sensors came in. The biggest challenge is this half-Cuban 8 maneuver here, where they fly completely inverted. Especially when over water like here, the GNSS signals reflect almost perfectly off the water. It comes down entirely to the INS and the algorithms to be able to track through that. So here's a visualization of the telemetry from one of the test flights as a pilot makes the customary 2 laps of the track. And you can see how everything is on track here as he's coming into the Cuban 8 maneuver, but as he goes inverted, everything goes haywire. You can see in orange the track of a high-end GNSS receiver from one of our competitors, and the green track from our own onboard GNSS. Both lose it as soon as the plane is vertical, and in fact, they don't recover for quite some time after the fact, after it's right side up again. And so the INS has to be able to track through that, and as you can see, here it does, coming right back through the gates at the end, at the bottom. Now, of course, those sometimes those GNSS outages are not just short-term outages, and that's where we get into GNSS-denied navigation. Now, I'll say right at the top that this is an open area of research and development. Don't let anyone tell you there's a silver bullet here, but there are a number of technologies that VectorNav is working to push forward with a variety of industry partners. The first is continuing to push the limits of what MEMS inertial sensors can do. As I mentioned earlier, the tactical embedded that you see here is a huge step forward in SWaP-C for a tactical grade inertial sensor, and has been designed to be, in the future, the navigation hub for a wide range of other technologies. Another critical part of the GNSS-denied solution space is avoiding losing GNSS in the first place. The tactical embedded supports plugging in an external SASM or M-code receiver, which prevents spoofing attacks. And we're supporting a few different projects developing smaller, more cost-effective anti-jam and anti-spoof antennas as well. Lastly, R&D continues into a wide range of other technologies that can provide aiding to an INS. And you see a picture of a self-driving car here, which is where a lot of this development is happening right now, utilizing everything from odometry to LiDAR to vision systems to radar. Obviously, all these same technologies can apply in an aerial context as well. Now, each of these sensors has their strengths and weaknesses. The cameras, for instance, they're cheap and small, but they take huge amounts of processing, and they can't see through clouds or fog. Radar is also cheap and small, but as Tesla has reported, a soda can with its concave bottom facing a radar can look like the size of a semi-truck to a radar. So there's some challenges there as well. LiDAR provides maybe the most reliable map of the environment of the three, but there's still ongoing efforts to make them small enough and inexpensive enough to really be used both in the self-driving car space, but also in the smaller UAV space. And critically, none of these technologies works under certain conditions like flying over water where there's nothing to see. But progress is being made, and while it may be some time before any system can match GNSS in terms of its overall accuracy and reliability and size and cost, there are plenty of missions today that can benefit from today's technology. As General Poss mentioned with the Reaper, even getting into today's smaller UAVs, we can at least get to the point where we can probably get you home if you lose GNSS. VectorNav continues to push these technologies forward on multiple fronts, and if it's something that you're involved with, we look forward to working with you to advance that state of the art. So I really appreciate your attention today. With that, back to Alan.
Thanks, Jeremy. You answered General Poss's questions about what can we do about spoofing and jamming. In a way, you said you're doing something, and but you can't give too much detail about exactly what you're doing, but it's good to know that there are countermeasures happening and available. Before we hear from Arthur Neves, want to encourage the audience to send in your questions. We'll have a closing question and answer session with the panelists after Arthur's presentation. Arthur Neves is Business Development Manager of Aviation for Spirent Communications. He started his career in the aviation industry, quickly achieving CF1, CF2, ME1, and ATP pilot licenses. And while flight instructing part-time, he earned his bachelor's and PhD from Rensselaer Polytechnic Institute, focusing on non-linear optics. With extensive work experience for Bell Labs Telecommunications, AT&T's Government Business Unit Advanced Technical Systems, Corning, British Telecom's Photonics, Northrop Grumman, where he ran a high-technology business unit focused on ISR missions for unmanned aircraft systems, SAIC leading their UAS initiative, formulating and documenting strategy for the UAS business, and finally joining Spirent in 2019 as Business Development Manager for Aviation in the Positioning Business Unit. He holds Part 107 UAS pilot license, continues to be an active pilot, having owned and operated several aircraft over his career. Arthur, please go ahead.
Thank you, Alan, for that great introduction. I appreciate it. Good morning, afternoon, evening, folks, wherever you find yourselves today. Today I'm going to give a brief overview of a methodology to capture GNSS RF in urban environments to fully understand areas of denied or degraded GNSS, review the state of the UAS market, GNSS uses and challenges, and a way to assure you have GNSS quality through Flight Check as a Service, which is an RF record and playback system mounted on a drone. Today, I want to introduce a methodology to validate position, navigation, and timing for a UAS platform or the airspace it operates in. Unlike manned aircraft, which primarily operate in clear sky, small UAS will often operate in an urban environment, which pose additional challenges for GNSS. In addition to lab testing, it is important to perform flight testing and capture real-time RF using a record and playback system. This data, along with simulation, supports the certification of drones through risk mitigation, complies with FAA performance-based standards, qualifies routes and vertiports, and aids in the UAS receiver qualification and selections. To further understand the use of this system, I will give a brief overview of the market, driving factors, and potential GNSS issues. The commercial UAS market is rapidly evolving and finding many uses, including infrastructure inspection, mapping, and ISR uses. Each of these applications have differing navigation and positioning requirements. For example, ISR and mapping may require centimeter level positioning, whereas real estate may only require meter level resolution. As the small unmanned aircraft system market matures, there are a number of factors that are driving the need for an automated traffic management system. First and foremost is the expected volume of the UAS traffic. As of August 2020, there were 1.7 million small UAS registered with the FAA, of which about 485,000 were commercial operators or applications. That number is expected to grow to 4 million registered commercial drones by 2026, and that's only just in the United States. By comparison, the total manned aircraft in the U.S. is about 220,000, of which 213,000 are general aviation and about 7,000 are air carrier aircraft. This huge volume and concerns over safety for beyond visual line of sight operations has driven the need for an automated traffic management system, which will include remote identification and unmanned aircraft service supplier implementation. Remote ID is the ability of a drone to provide identification information that can be received by other parties. The USS provides for traffic deconfliction, airspace compliance, national airspace coordination, public safety, UAS operator management, and surveillance. The reality is that a notice of proposed rulemaking for remote identification for small UAS was released in December of 2019, and a final rule is expected in December of 2020. Concurrently, the unmanned aircraft's service supplier pilot program demos are being held under the FAA's pilot program in October of 2020. It is expected that USS implementation will also start in December of 2020. Both ANSI, ASTM, and other standard bodies are rapidly being developed for UAS and will assist in the management of increasing numbers of UAS operations. As a primary means of remote ID and navigation rely on GNSS, there are a number of challenges that need to be considered. The first, commercial operations such as infrastructure inspection, mapping, ISR will need to comply with regulations or utilize shielded operations when operating in controlled airspace. The reality of it is that GNSS is critical for both safety and efficiency of operations. Loss of GNSS can have significant consequences, as the common example of the drone that lost GPS in an urban environment and drifted, lost command link, and wound up landing feet away from a runway at a Class B airspace. The reality of it is, if it flies, it must position, and if it positions, can we trust its position? First of these challenges is that the UAS will be operating under Part 107, below 400 feet AGL. This is a complex environment for GNSS for several reasons. A clear view of the sky is not always available. Buildings and other obstructions can block or obscure the signal or create multipath effects. It's a very dynamic environment. Real-time autonomous integrity monitoring WAS, or Wide Area Augmentation Service, and RTK, or real-time kinematics, do not address this environment well. This results in a need for localization and navigation fusion of multiple sensor types or an accurate forecast of GNSS to avoid areas of denied or degraded GNSS. Second of these challenges is the small UAS will be operated beyond visual line of sight. In this case, the pilot in command may not rapidly detect abnormalities. There may also be flights over people, creating the need for solid risk mitigation. So better planning and integrity is needed. Third, the unmanned traffic management is both a dynamic and automated airspace management system. For it to function safely, it will rely on accurate and reliable navigation reporting and performance. These functions will be used for traffic deconfliction, airspace compliance, national airspace system coordination, public safety, UAS operator management, and surveillance. Fourth, the GNSS in combination with an IMU, or inertial measurement unit, is used for flight stability and navigation on the UAS. This is going to require high accuracy and integrity requirements. Augmentation services such as RTK, precise point positioning RTK, and PPP help GNS with orbit errors, clock errors, ionospheric delays, and tropospheric delays, but do not address multipath or obscuration. For these reasons, it is important to know when and where GNSS performs, or supplement GNSS with other sensors such as LiDAR and radar. Supplementing GNSS with other sensors adds cost and swap considerations for small UAS. Having accurate GNSS, you can provide more dynamic use of the airspace volume by having accurate knowledge of your position area, clearly defining your well clear volume, remaining within the operational design domain. Not only are military, commercial, and consumer end users becoming more reliant on a continuous accurate GNSS signal, they're also becoming more reliant on it at a time when the amount of signal interference and a number of different types of signal interference are both increasing. Atmospheric effects, multipath effects from the signal bouncing off structures, and obscuration by terrain like mountains, buildings, deep cuttings, for example, like in open pit mines, and dense foliage have always affected GNSS signals. But now man-made sources of interference are increasing too, ranging from intentional or unintentional jamming, interference from nearby cell towers, and even sophisticated spoofing or broadcasting of fake navigation signals. As seen here in the picture in the lower right, Spirent's Spirent's drone, or Flight Check as a Service solution, which records the navigational performance of several receivers under test, ground truth using a high-end receiver and IMU, and real-time GNSS RF as a function of location, altitude, flight envelope, and time. Position, navigation, and timing is not a given. There is a need for another level of assurance. GNSS quality of signal can also be taken into account to ensure the UAS position error is known and properly managed to mitigate risk and ensure a safe operation. One of the outputs is the ability to assess performance through the generation of a GNSS heat map. One way to increase position accuracy and combat the threat of GNSS interference is to have the receiver support either multiple navigation satellite systems or multiple frequencies of the same satellite system, or both. Increasingly, manufacturers are developing multi-frequency, multi-GNSS chipsets that can process not just standard GPS signals, but signals from other global navigation satellite systems like GLONASS, Beidou, Galileo, and regional systems like Japan's and India's. Multi-GNSS systems demand more intensive field testing to understand the performance of the receiver in different locations around the globe. This is another area where record and playback can significantly accelerate testing by using recordings of the signal environment in different areas around the globe. Choosing a good route with good GNSS minimizes the position error, whereas choosing a route with degraded GNSS results in a much larger position error, requiring a clear airspace volume. Test flights can be made much more efficient by using record and playback system to capture live flight data and replay it later in the lab. This greatly reduces the system risk and can add in the UAV certification process. Customers are interested in understanding how well the receiver will cope with high winds, multipath effects, atmospheric interference, signal obscuration, and vibration and tilting of the UAV in flight. We can use the record and playback system to record and replay live flight test data in the lab, removing the need for additional flight tests. Another GNSS performance consideration is the evaluation selection of the most appropriate GNSS receiver for the vehicle. There are many receivers available on the market with huge differences in cost, sophistication, precision, and accuracy. Design teams should conduct their own independent testing of individual chipsets and receivers. Another thing to consider is a GNSS chipset or receiver placement. That is, where within the design should the GNSS receiver sit? Is it adequately isolated from other RF noise that could affect the signal? Antenna design and placement. What sort of antenna do we need to ensure continuity of GNSS signal reception and to mitigate against signal interference? Where should the antenna be placed for optimum performance? Test teams will want to consider a multitude of performance aspects, many of which will depend on the intended real-world use of the UAV. For example, a UAV designed for precision ISR will require a far greater degree, e.g. sub 10 centimeter of position accuracy than a UAV designed for parcel delivery. Fundamental tests include time to the first fix, which is a measure of how quickly a receiver performs the signal search process, acquisition sensitivity, tracking sensitivity, reacquisition time, static navigation accuracy, dynamic navigation accuracy, which is the same as static, except the receiver is undergoing motion in any of all or the three axes of movement, and the timing accuracy. And it's not just the design of the drone itself that has a bearing on its ability to calculate its position, hold a position, and navigate accurately in the real world. Critical considerations for designers and test teams include wind. In other words, can the UAV quickly regain its intended position if blown off course? Temperature changes. Do the GNSS antenna and receiver continue to function as expected in extreme temperatures? Signal obscuration. Can the UAV still generate an accurate position when signals from one or more satellites are obscured? Signal denial. Can the UAV continue to generate an accurate position when GNSS signals are completely denied? Multipath effects. In other words, can the UAV recognize and correct for multipath effects caused by the GNSS signal bouncing off of tall buildings? Latitudes near the poles. If flying at high latitudes where there are fewer or no satellites overhead, can the vehicle still calculate its position accurately? And RF interference. Can the UAV detect and correct appropriately for a wide range of potential sources of RF interference? Spirent's testing solutions, GNSS forecast as a service, and future services will help pave the way for the next generation of advanced air mobility. In the next decade, it is expected that electric VTOLs, or vertical takeoff and land vehicles, will become a reality, freeing up traffic congestion and providing environmentally efficient vehicles, thereby minimizing pollution. It's expected that these autonomous vehicles will incorporate GNSS as a means of navigation and control. Having the tools in place to assure GNSS accuracy will ensure safe operation. Bringing a viable UAV to market for commercial and military use presents many challenges for test teams at all stages, from the R&D through to production. These UAVs are heavily dependent on satellite-based positioning technology, and anything that impacts the GNSS receiver's ability to do its job will in turn impact the UAV's ability to fulfill its own intended purpose. As a result, Testing of the positioning capabilities of UAV must be thorough, rigorous, and broad to ensure that as wide a range as possible of potential real-world conditions have been applied. This is only possible with a test program that incorporates lab-based simulation and record and playback with live flight testing. Not that having only GNSS is the bad thing, it just means that you need design and operate it correctly. Knowing where GNSS is reliable solves a big problem. That's one of the reasons that people use a ton of different equipment, is that you don't know where GNSS won't work. And that's what Spirent hopes to solve. Thank you. Back to you, Alan.
Thank you, Arthur. I have a few tidbits, more than tidbits, substantial bites for our audience, resources to follow up on some of the ideas and concepts presented in this webinar. Lots of follow-up possibilities and access to deep data, deep information. Lori, one final question for our audience, please, before we turn to questions from the audience.
Absolutely. On the screen, our third and final poll: what is the leading challenge faced by your UAS application? Got 4 choices there: obstructed flight environment, jamming interference, high dynamics or shock in flight or launch, or finally efficiency or accuracy of data capture. All right, 36% obstructed flight environment, 26% jamming interference, 7% with high dynamics or shock in flight or launch, and 31% efficiency or accuracy of data capture. Any thoughts on this one?
Well, equal concern, or roughly equal concern, with obstructed flight environment, which is generally the first question that comes up in any kind of UAS operation, being highly dependent on GNSS. And then, of course, we want to know about the reliability and accuracy of our sensors. Jamming and interference is going to always be a concern. I guess in our audience, at least, we have fewer people using catapults or tube launchers from airborne platforms. Speaks to the probable commercial bent of our audience, at least for today. There's been a lot of interest in the flight check as a service, but before I turn to those questions, Arthur, I'm going to give you a chance to catch a longer breath and ask Jeremy a couple of questions. One listener wants to know, what's the velocity accuracy of your VN 210 and 310 models when GPS is not available for long periods?
Yeah, that's a good question. So VN210 and VN310 are 2 of our tactical grade GNSS INS systems. The GNSS receivers on board are going to give you velocity accuracies when GNSS is operational on the order of 5 centimeters a second. And that's going to degrade on the order of 2 or 3 millimeters per second squared. So something like you'll be out at about 20 centimeters per second, uncertainties out at about a minute, and growing pretty linearly from there, to give you some ballpark numbers on that.
All right. And if you could just review briefly, Jeremy, the reasons for the small size of the devices. Should be evident, but just to cover them again. And then what are the limitations and challenges of a small size module? Clearly they have advantages. What do you have to play those off against?
Yeah, that's great. So yeah, I mean, and I made a quick reference to it, but definitely worth reiterating. You know, every particularly for aerial applications, every gram or every watt or milliwatt that you're spending on your navigation system, you don't have available for the rest of your vehicle. So whether that's something that you want to stay airborne longer so that you can collect more data, or you want to be able to direct that at having a bigger, better LiDAR, bigger, better camera so you can more efficiently collect data, or you know, otherwise complete your mission. Basically, for aerial applications, you want to drive size, weight, and power down as much as you can. As far as the challenges that come with that, it is, I'll talk specifically to MEMS technology. MEMS devices are sensitive to mechanical stresses, thermal stresses, things that are flexing the MEMS substrates themselves. And so it's a lot easier to isolate those from the surrounding environment and keep them from being flexed when you can put a big metal box around them and otherwise isolate them. So driving down the size, particularly with our tactical embedded, to the 15 grams and just an inch square or so, took a lot of efforts to minimize those impacts and figure out ways to overcome those effects, so that we can shrink it down to an even smaller size than anyone's done before, while maintaining performance even in real-world conditions.
Thanks. Turning now to flight check as a service, Arthur. In performing flight check as a service with record and playback, do you see much change in GNSS signals over time?
Yeah, that's a excellent question. One of the things that a lot of people tend to forget, they often consider that the vehicle's moving, but you also have to take into account the fact that the satellites are actually moving at around 14,000 kilometers per hour. So certainly over a period of a couple hours, you'll see a significant change in the number of satellites available and the qualities of the signals. And we noticed that a lot for one of our customers that's using it from mining applications, whereas, you may be able to operate on one side of the mine at 10 o'clock in the morning, but on around 2 o'clock in the afternoon, you may need to move to the other side of the mine.
How about in that same respect, not sure if I'm understanding the questioner's question accurately, but asking about altitude, signal quality change relative to altitude.
Yeah, that's another great question, and it may be more intuitively obvious to a lot of people, but when you're down, particularly in an urban environment where you have obscuration and multipath effects, the lower you are, the less visibility, and as you go up in altitude, we start to see a significant increase in the number of satellites available. And then once you get above the level of the buildings, you're basically operating in clear sky, which is what all manned aircraft operate in pretty much full time.
Terrific. Jeremy, turning back to you, can you place an INS on the inner axis of a gimbal to provide both stabilization and georeferencing to remove the need for encoders?
Yeah, that's a great question. Let me take a quick step back with that one. When you're looking at a gimbaled system, the encoders can pose problems for really high accuracy applications at really high altitudes because of the quantization errors that you get with encoders. And so having an INS on that internal axis of the gimbal is pretty critical in those applications, as well as providing gyro angular rate feedback for your controller, which is also important for maintaining stabilization. The tricky part is that in order for a GNSS INS to operate correctly, you really need the GPS antennas to be fixed relative to the inertial sensors. And so if you have the inertial sensors rotating in the inner axis while the GPS antennas are up on the aircraft, on top of the aircraft, then you're violating that link. So one of the best ways to, if you're really chasing the best performance, is actually put a full GPS INS on the aircraft or in the base of the gimbal, and then a second inertial sensor purely on the inner axis, and then you can basically provide transfer data between the two. A couple different options that we have for doing that to track the gimbal angles very accurately without ever having to map through encoders.
All right. Thanks very much. Well, we are reaching the end of our hour and a half, and but we'll be back. We are going to be back tomorrow and Friday. We have promised you a full week, and we're giving you a full week's worth of material in only 3 days. Tomorrow, tune in at the same time, same station. Don't touch that dial. We're going to be talking about machine control, autonomy in heavy construction and mining. We're going to be talking GNSS, of course, inertial corrections, beacons, platforms include autonomous heavy equipment, and in terms of software reality capture and data management. On Friday, a very big day for many reasons, but we have a special reveal in store for you in the precision agriculture realm and autonomous ground vehicles. We'll be talking again, GNSS, our constant theme, inertial corrections and perception sensors. Here's the clue as to what you're going to see: a tractor, and a very talented tractor at that. We're going to be talking data fusion, situational awareness through precision perception, and lots more. Hope you'll join us. Hope you'll tell your friends and colleagues that we have a lot more to offer this week as we continue through our Autonomous Week. Well, I want to thank the audience for attending, and I want to thank our sponsors, VectorNav and Spirent, for making this webinar possible. I want to thank our speakers, General James Poss, Jeremy Davis, and Arthur Neves. And with that, I will turn it back to you, Lori. Thanks again to the audience. Stay safe, and best wishes.
Okay, well, thank you, Alan. And once again, thanks for joining us. This is Lori Dearman. Hope we see you tomorrow. Have a good one.